Hi and welcome to MSc. In this video we're going to be looking at a physics pulley problem, specifically an example where there's two hanging masses. So this is a fairly classic high school physics problem where we have a pulley and two masses hanging from it, and we're asked to find the acceleration of the blocks. So there's a couple things we need to remember about pulley scenarios. First, generally we're going to treat these as frictionless. In other words, there's no forces of friction that I need to include in it, and as a result, tension throughout this rope and pulley system is constant all the way through. So what does that mean for us here in this problem? Well, if we start labeling some forces on these two masses, we can see that we would have a force of gravity acting down on this mass. I'll call this W2 for the weight on the second mass, and here we have a force of gravity pulling down. I'll draw this one slightly longer, and I'll call this one W1. And the reason I drew this slightly longer is because it's a bigger mass. Okay, so intuitively, we think that this might accelerate down on this side and up on this side. So what other forces are at play? Well, there's tension forces, right? Connecting these two together. Now, sometimes you'll see tension forces drawn from the contact where the rope joins the object, and sometimes you'll see it drawn from the center of mass, depending on what your textbook and teacher prefers. Okay, I'll draw it from the center of mass here as though it were a free body diagram, where we would just represent it as a dot and have both of them acting off the same point. So we have a tension force here, and because it's the same throughout the whole system, I also have a tension force here. Now this tension force should be equal in size to this first one. So this and this line, or vector, should be equal. Okay, now we need to set our direction. And this is where things get a little bit interesting, because we know that this block, the heavier one, is going to fall down, and the lighter block is going to move up. So really what we have is some type of curved forward direction where we can say, look, that is my x direction. And that's a weird thing to say, that we have this curved forward direction. So it is possible, if that bothers you, to redraw this one a little differently. And we can actually, because we're not worried about the friction of the pulley at all, we can redraw this removing the pulley. And that diagram would look something like this. First, we'd have our larger block there. Then we draw our smaller block. And lastly, we would draw the rope joining the two. If we do it this way, well, then our directions make a little bit more sense. I can draw an axis that would look like this, where this would be my x direction in the direction of the positive, or the larger block, and the y would be vertical. We've removed the pulley in this scenario. What makes this a little bit more complex sometimes for students is now in this scenario I actually have weight vectors that don't go up and down. They go left and right. And that can sometimes cause some confusion for students. And so if this helps you, that's tremendous. And if it doesn't, then you can just use the kind of curved forward direction, or saying forward is down on this side and up on this side. And we'll have our two tension vectors drawn here again, and again they should be equal and in opposite directions. So whether or not you want to redraw this, or whether or not you're okay with having this weird forward direction of down on one side and up on the other, we can now start to apply our formulas. And what we know here is we know that the net force has to equal mass times acceleration. And we're looking to solve for this acceleration. The question is, what mass do I have? Well, it's both masses that are accelerating, so I'm going to call this m sub s for the mass of the system. You could also say total mass, and that would be fine. So here we have ms is equal to mass 1 plus mass 2. Okay, well, what forces do we have? Well, the net force is equal to the sum of all the forces. Whether or not you have this diagram or this one, you'll notice that the net force is only in the x direction. So really it's just the sum of the x direction forces. Well, what are those forces? Well, those forces, and when I draw this out, or when I write this out, I typically start with what's driving the whole system. Well, what's driving the whole system forward here is the larger weight. Right, the larger force of gravity acting on M1. So I would say, well, that's pulling me in the forward direction, and this tension force is resisting it. So I'll put negative, already taking into account the different direction. On this side, then I have a tension force pulling it in the positive direction. And then I have this weight, which is in the opposite direction. And you can see that's opposite the up motion that I'll have, or in this diagram, it's clearly pulling back. So it'll be negative W2. One of the things you'll notice right away here is the tension cancels out, right? And that's again because the tension is equal and opposite in all directions here in this system. Okay, we actually have tension forces pulling down on this pulley on both sides. And so whatever's actually holding this up requires a force that's twice the tension to hold it up. But because they're in equal and opposite directions here, we can say that they cancel out of this formula. So the net force is this mass of the system times acceleration, and this is actually equal to the difference in the weights. Now the weight is really just the force of gravity. You might even call this Fg, perhaps. And so what we have here is m1g minus m2g. And now if we're looking for acceleration, we will rearrange and solve for acceleration by dividing both sides by the mass of the system. So we'll get the acceleration is equal to m1g minus m2g all over the mass of the system. So if we put some numbers in here, this would be 7.5. I'm going to use 9.8 for my gravitational acceleration, my gravitational field strength. I have 3 kilograms here, and again 9.8, and we're dividing by 7.5 plus 3. And if we do this, I'm going to put this over here. My acceleration is going to be equal to 4.2 meters per second squared, and this would be in some type of forward direction. It would be down on the left and up on the right, or in our positively defined forward direction. Okay, this has two significant figures. It works out to be evenly 4.2. In this problem, I would round to two significant figures because of my 7.5. Okay, and we always round to the lowest number provided in the question. Okay, so that's how we handle this, and you'll notice that the tension, even though we had to kind of acknowledge it, drops out of the problem altogether. And that's how we calculate the acceleration of this system. I hope this short video on acceleration of hanging masses with pulleys has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you so much for listening and watching.